I'd like to acknowledge my collaborators, not only Saul Tukolsky from Cornell, but also many people in the Simulations of Extreme Spacetimes collaboration. There's our website. And we now have 8 institutions involved in this collaboration. So just a short outline of my talk. I'm going to start with an introduction motivation, especially for those people who might not be astronomy or LIGO people in the audience. Then I want to talk about current simulations that we've been running on blue waters for support of LIGO science using a code called SpEC, and then an upcoming code called SpECTRE that we're now testing and that we'll be using much more in the future. Okay, so gravitational waves are ripples in curved space-time. They were predicted by Einstein over 100 years ago, and they should be emitted by any objects that or energy that's moving in a sufficiently complicated way. My fists would generate gravitational waves, but they interact very weakly with matter. So if you want to detect gravitational waves from my fist, you're out of luck. You need something a little bit bigger, like say solar masses. You need something moving a little bit faster, like half the speed of light, in order to actually directly detect gravitational waves. So with that motivation, the NSF's largest project, LIGO, was built. There are 2 detectors in LIGO, one in Hanford, Washington, which here, you can see it's all deserty with tumbleweeds, Livingston, Louisiana, which is here, which is all foresty, swampy with alligators. And the theorist version of how this works is you have a laser that gets split by a beam splitter and goes down interferometer arms, which are 4 kilometers in LIGO, and then they recombine at the beam splitter and interfere at the photodetector. And the gravitational wave coming in will make these mirrors wiggle a little bit, and then you see the signal in the photodetector. So that's the idea. And then in 2015, this is the event that shook the world, and literally it did shake the world. It shook the world to about 1 part in 10 to the minus 21, which you can see here on this vertical axis of this graph. The LIGO detectors are the only thing that were able to detect that small shaking, and so here are the signals in Hanford and Livingston, and as a function of time. And this signal was caused by 2 colliding black holes 1 billion light years away. The masses were in the 30 solar mass range. I like putting up some of these, astronomically large numbers. This is one of the most powerful events ever seen by humans. The total energy is 10 to the 54 ergs. Supernova are in the 10 to the 51 ergs. So that tells you about the power emitted and the energy emitted by this thing. This is an image from one of our simulations that shows 2 black holes. This is the shadow of the black holes. This is what you would actually see if the 2 black holes are in front of your galaxy. This is following light paths from the background stars curving around the black holes going to your eye. Okay. And of course, this led to the 2017 Nobel Prize in Physics. So the question is, how do we know that these waves came from black holes? How do we know the masses, et cetera? And the way that we know this is that we compare the signals that LIGO measures to predictions of general relativity. Well, how do you get these predictions? Well, some of these predictions of general relativity you can get in an approximate perturbative way, say when the 2 black holes are very far apart, and you could expand in powers of V over C, so on. But to get the entire signal, you really need numerical relativity, numerical simulations where you solve the Einstein equations in full 3D on a computer. And so this is another plot from the first detection paper, and in this shaded gray is the LIGO data that's been smoothed out and corrected for noise, and in red, this shows one of our numerical relativity simulations that matches up very well. Okay, so we'll get back into parameters. We were just hearing that at the end of Roland's talk. So the parameter space that I'm talking about is 7-dimensional, because what I'm doing is I'm ignoring eccentricity. So for eccentricity, you add 2 additional parameters, the eccentricity itself, and an angle describing the angle of the eccentricity ellipse at a particular time. So there are 7 parameters, intrinsic parameters, the mass ratio, and these 2 spin vectors. And the idea is that different parameters will give you different gravitational wave signals, and by comparing, and this is how you do parameter estimation, is that you compare predicted gravitational wave signals and try to get the best match to get the parameters out. Okay, so that's basically what we're going to be doing. So the second part of my talk will describe the SpEC code and how we simulate black hole binaries. So SpEC is the spectral Einstein code, a code that we wrote probably a decade ago or so. It's been under development for about that long. And it solves Einstein's equations, which we write. You could write it several different ways, but you could write Einstein's equations as 50 coupled nonlinear first order partial differential equations. And there are other numerical relativity codes other than SpEC. SpEC is unique in the sense that it's the only one that uses a spectral multi-domain method, which gives it higher accuracy than other existing codes. So the idea is that you have this computational domain. This is just a 2-dimensional slice to the 3-dimensional domain with 2 holes cut out of it. Those holes are inside of the horizons. We cut out those holes so that we don't need to worry about that singularity that's inside of black holes. It's kind of nasty when you have singularities on computers. And you divide up your domain into a bunch of different subdomains. And each one of these subdomains solves your 50 partial differential equations with boundary conditions that are communicated from the neighbors, basically using a characteristic type method at the boundaries. Here's another view of our grid, again, a 2-dimensional slice of our grid with 2 horizons that are also shown. These 2 horizons are shown shaded red. This is a case where you have an 8-to-1 mass ratio. And you also see a common horizon. This is just at the point of merger. That's in light gray. You could probably barely see it, that this other horizon encompasses the 2 inner horizons at merger time. And the reason I wanted to show this is you could see how the grid distorts in order to follow the shapes of the horizons as the horizons evolve. And now we don't decide what the shapes of the horizons are. Einstein does. They're whatever they are, and we have to make the grid follow them. We have both p refinement, where we refine the polynomial order in each one of the subdomains, and h refinement, where we can break up subdomains into pieces. Okay, so the computational cost of a simulation depends very much on the parameters. So for easy parameters, and by easy I mean mass ratio that's about 1 and spins that are pretty small, one of these simulations takes roughly 4 days on 3 nodes of blue waters. For hard parameters, so crank up the spins near their maximum or make the mass ratio sufficiently different than 1, say around 8 to 10 is about the highest that we ever have gone so far for normal simulations. Takes about a few months for one of these simulations. So what we want to do is remember that the different values of parameters give you different signals, so you want to search through this entire parameter space. So we run hundreds of these things simultaneously on blue waters and also on other resources like Exceed. So here's one of our key results is the Waveform Catalog. This is a publicly available waveform catalog that currently has about 300 simulations in it. We're going to upgrade this to about 1,800 simulations. We're in the process of writing a paper that will describe this. As soon as this paper is submitted, then these will be made public also. This shows the 1,800 something simulations. This includes 542 that were run recently on blue waters and does not include an additional 640 on blue waters that are either in progress or have just finished, but they're going to be part of the next step. And these waveforms have been used by LIGO scientists, have been used by other people who are studying black holes and binary black holes. For example, in the last talk, Roland put up a slide where one of the example waveforms for LIGO was from this catalog. As another example, this is the discovery paper, and this red numerical relativity waveform for Hanford, the same one in Livingston. This one is one of the simulations from our catalog. Okay, here's another thing that we want to do, and that we have been doing. So the problem with the simulation catalog is that each one of these simulations takes sometimes weeks, sometimes months, and it's a very large parameter space. But what LIGO really wants in order to do parameter estimation is they want to search over a whole bunch of parameters all at once. They want to evaluate one set of parameters in 50 milliseconds, not 50 days. So what we do is we run as many simulations as we can, sampling the 7-dimensional parameter space in some intelligent way. And then we build what's called a surrogate model. The reason it's called a surrogate model is it could stand in for the and take the place of the numerical relativity simulation. A surrogate model is basically an interpolant that interpolates in parameter space between the simulations that you've already done. So our latest surrogate model, I'm showing you some results here. I'll explain what this is in a second, involves 744 simulations. Most of these were done on blue waters. The simulations are limited to mass ratios less than 2 and spins less than 0.8. And the reason we did that is just to cut down the number of simulations. This surrogate model is publicly available, and we are improving it. In particular, we have another 640 runs on blue waters that go up to mass ratio 4 that we're using to make yet another surrogate model that's in progress. So let me explain what this graph is. This here is a histogram that shows error. This mismatch is an error, so the right side is large errors and the left side is small errors. And this histogram is made up of comparisons between simulations and various models that are supposed to mimic those simulations. So in this orange and green, what you see are at the time we published this, the current waveform models that are used by LIGO. And you see their errors. And here is the error of our surrogate model, about 2 orders of magnitude better. And for comparison, this dark black curve, this is the numerical error that we get in our simulations themselves by comparing different resolutions. So we're doing better than any of the other models. Okay, I'm going to shift gears now and talk about neutron-star binaries and SpECTRE. So another event that shocked the world, maybe even more so, was this detection of a neutron-star binary. And the reason this was so important, not only was it the first neutron-star binary, but you also see this throughout the electromagnetic spectrum. So in the same way we want to do binary black hole collisions and simulate those to compare with LIGO, we want to do the same thing for neutron-star collisions. And this is more difficult than black holes because you have to include a lot more physics here. And SpEC, the code I was just been talking about, can do binary neutron-star simulations, and Roland was one of the key people who worked on that for a while. But SpEC and other codes that do this aren't still quite accurate enough for LIGO. So we are building a new code called SpECTRE, and this is going to be basically the next step from SpEC, but it has some key differences aimed at performance and scaling. The one that I want to tell you about here is task-based parallelism, and we're doing this using this Charm++ infrastructure developed at Illinois. And the idea here is that instead of a message passing type thing like what SpEC does, Each one of your subdomains, these are the light blue, and interfaces, which are the purple, are distributed into some global object space, and there are operations that have to be carried out on them that are divided into tasks. And the runtime system will take these things in the global object space and divide them into cores however it wants, and it will execute tasks as the dependencies of those tasks become available. And this is a way to avoid a lot of the performance bottlenecks, especially a lot of the load balancing problems that we have in our current code. And just let me give you an example. This is a small example on a local cluster where we only have 12 cores that we ran this on. What this is one of the Charm++ tools that shows you what the processes are doing on the vertical axis as a function of time on the horizontal axis. So for instance, at this early time here, you see this big vertical dark blue thing. That tells you almost 100% of the processors are doing computing volume terms. And here, almost 100% are computing the interface fluxes. And what you see is that as you go in time, the processors become desynchronized, but that's okay. There's no idle time where they wait for each other. If you did this with MPI and message passing, often what happens is you get to a point where everybody's computed fluxes except for one or two guys over there, and then everybody has to sit there and wait. That's what happens in our current code. Here you don't have to do that anymore. So that's the idea. And this is another relativistic MHD test problem that we did on SpECTRE. In this case, we briefly took the entire blue waters and ran a strong scaling test. This is for a particular, this is actually a 2D problem, which we ran in 3D by having just 2 or 4 elements in the z direction, but it was just to demonstrate that we can scale up to the entire blue waters depending on the configuration that we use for Charm++, at least for this test problem. So I'm about to end. Let me just summarize. Basically, we need numerical solutions of Einstein's equations in order to understand LIGO data and in order to do better parameter estimation. I told you about some current simulations using our code SpEC designed for binary black hole problems, and the hundreds of simulations that we're doing on blue waters right now for gravitational wave science. And also I showed a few tests, scaling tests of prototypes of our next generation code, SpECTRE, that's motivated by neutron-star problems, but we could also do this use SpECTRE for binary black holes. And the key ingredient, or one key ingredient, is task-based parallelism for scaling. And the outlook for the future is just want to let everybody know that people probably know this already. LIGO sensitivity is improving. There are new detectors planned. LISA is being planned, which is going to have a signal-to-noise factor of 100 better than LIGO. So we need more simulations and more accurate simulations. And so we're working towards that. So thank you.